Chapter 23, Electric Fields. This is the first chapter of electrostatics, and in this chapter, we're going to study the basic concepts of electric charges and electric fields. We're also going to learn how to calculate the electric fields and electric forces produced by electric charges. We all know that electric force is one of the most fundamental forces of nature. The one we studied before that was the gravitational force in Physics 1b. Now, we know that it takes mass to have a gravitational attraction, right? You need to have two masses so that they can attract each other gravitationally. So, what does it take for two objects to attract or repel each other electrically? Well, common sense tells us that it takes electric charges. I have here a very simple demonstration. These are some small pieces of paper. Now, here's a piece of plastic. I'm trying to pick them up, okay? And you can see nothing happens, right? Now, watch what happens. I'm sure many of you have seen this before. If I were to rub this piece of plastic against my hair. Okay. That was my head, okay? And that's what I'm going to do. I'm going to rub. Okay. I'm going to rub. Okay. And then I'm going to try to pick up the paper scrap. See what happens. Nothing happens, okay? Maybe I didn't try hard enough. Okay, I'm going to try it again. Still nothing happens? Now there we go. You see that? Okay. It is now picking up the paper scrap. Okay. Try it again. And doing it even harder. See here? It is picking up some more. Okay. So what is going on here? Well, obviously there's a force of attraction between the plastic and the paper scrap, and that force certainly is not gravitational because there is no such strong gravitational attraction to go against the gravitational force of the Earth. This is a small example of electric forces. In this case, the forces are attractive. So how come the force is attractive? Well, it turns out that there are two types of electric charges, which we designate as positive and negative. And if a positive charge and a negative charge meet each other, they're going to they're going to attract each other. And what happened in the demo was that by rubbing the piece of plastic against my hair, there was a charge transfer. So some electrons went from the hair into the plastic, making the plastic negatively charged. Okay, now on the paper scrap, the net charge was 0. But as you move the negatively charged plastic towards the paper scrap, it causes an attractive force on the positive charges on the paper scrap. And that's how the paper scrap was picked up. But we also know from many other demonstrations that sometimes electric forces can be repulsive, and that happens when you put a positive and a positive charge together, or a negative and a negative charge together. So overall, we know that a positive charge and a positive charge would repel each other, right? A negative charge and a negative charge will repel each other, but a positive and a negative charge will attract each other. So, in general, unlike charges attract each other, and like charges repel each other. This is the reason why we know there has to be two types of electric charges, positive and negative. This is to be distinguished from the case of the gravitational force, which is always attractive. So there is no such thing as negative mass. Otherwise, there would be a what's called repulsive gravitational force, which we know does not exist. Now, electric charges, just like masses, are conservative, which means when you look at the total amount of electric charges in an isolated system, you'll find that whatever happens, the total amount of electric charge, positive plus negative, is always the same. It will never change with time. Everything should be accounted for. Now, the central law in this chapter is the so-called Coulomb's law, which describes the electric force between 2 point charges. So let's study Coulomb's law. Coulomb was a famous French physicist. Again, it describes the force between 2 point charges. By point charge, I mean a charge with negligible shape and size. So it's like a point. So here we have a point charge, Q1, the amount is Q1, and another point charge, Q2. And there is a distance, r, between them. And I can draw a vector pointing from charge 1 to charge 2, which we call vector r. It is clear that the force between these two charges, the electrostatic force between these two charges, must depend on the charges Q1 and Q2. It must also depend on r, the distance. Now, before we introduce Coulomb's law, let's look at certain aspects of the law. First of all, let's look at the so-called symmetry considerations about Q1 and Q2. If we write Coulomb's law, force is a function of Q1, Q2, and whatever. How should it depend on Q1 and Q2? Well, we know one thing that is clear, and that is it has to be symmetrical about Q1 and Q2. For example, you cannot possibly write F equals to something times Q1 squared and times Q2. That would be just wrong. Okay? How do we know for sure it's wrong? Because it is not symmetrical against Q1 and Q2. And what is wrong with that? Because suppose this is the force between given by 1 on 2, okay? And let's say it's something like Q1 squared times Q2. Then what about the force between given by 2 to 1? That would, by symmetry, have to be equal to Q2 squared times Q1 times some sort of constant, right? But wait a minute. This is the force given by 1 to 2. And here's the force given by 2 to 1. Isn't that a pair of action and reaction? And according to Newton's third law, what can we say about the magnitudes of these two forces? Yeah, they have to have the same magnitude, right? But you see, these two expressions will not give you the same result. So what does that tell you? It is not possible to break the symmetry between Q1 and Q2 in the expression for F. If it's Q1 squared times Q2, it must be wrong. You can think of something like Q1, Q2, or Q1 squared, Q2 squared. That is possible, but certainly not asymmetrical about Q1 and Q2. These are wrong, okay? Secondly, let's look at the so-called universality of charges. What does it mean by universality? Well, we know in 1B we studied so-called gravitational force. It is the so-called universal gravitational force. Why do we call it universal? Because anytime you have a mass, you can attract other masses. And we know everything in the universe has a mass, right? So everything in the universe can attract everything else gravitationally. That is why we say the gravitational force is a universal force. What about electric force? Is electric force universal? In other words, does there necessarily exist an electric force between one object and another object in the universe? Well, the answer is no. Electric forces are not universal because not everything has a charge, even though everything has a mass. Okay, so the universality of charge is not present, unlike the universality of mass. That's something we keep in mind. You must always have gravitational force between two objects, but they may not have electric forces unless both objects have net charges. Okay, another thing we look at is how it depends on R. How does the force depend on R? We know that when it comes to gravitational force, the force depends on the distance between the 2 point masses as 1 over r squared. Remember that? We call it inverse square law. Now, why does nature choose an inverse square law for the gravitational force? We don't know. Okay, but is this the only invert square case? Well, it turns out not quite. It turns out that nature quite prefers the invert square case. In fact, even for the electric force between 2-point charges, Coulomb's law tells us that it depends on the distance r in the exact same manner. In other words, the so-called inverse square manner. So the force between Q1 and Q2 should go like 1 over r squared. And again, why is that? We don't know. Okay, we don't know. But one thing is clear. The inverse square law, this particular power factor, r to the power -2, behaves unlike any other power factor. This will become clear in the next chapter when we study so-called Gauss's law. Okay, another thing about Coulomb's law is that there is a constant, just like the gravitational force, there is a constant in front of it, and that constant turns out to be a very, very large number, about 9 billion in SI system. And let me explain to you the units here. Newton times meter squared over Coulomb squared. And the reason why they have such a fancy unit is because you must balance the units of both sides. So at this point, why don't I write down the Coulomb's law? Of course, it's also in the textbook. Coulomb's law is the force that tells you the force between 2-point charges, Q1 and Q2. It says force given by 1 to 2 equals to this constant Ke, okay? And then Q1 times Q2, you see the symmetry between Q1 and Q2, divided by r squared, and there we go. That's the inverse square law right here. And Ke is that constant in front of it. This is the famous Coulomb's law. Oops, this is only the magnitude, and I have to find a direction as well. We'll do that just a little bit later, okay? So this is only the magnitude part. Now, again, why does K, this constant, have such a funny unit? Well, it's because it has to balance the units of both sides. You see, this is Newton, right? This is force in newtons, okay? You move that r squared over. R, of course, is in meters, so you go meter squared. Then you divide it by the units of charge squared, right? You move that over. Now, what is the unit of charge? The SI standard unit. Well, you must have guessed it, I'm sure. Every time we introduce a new fundamental concept in physics, we name it after a physicist, right? Like force is named after Newton, and what do you suppose charge should be named after? Well, of course, Coulomb, right? Because of Coulomb's law, see? So the fundamental charge unit in SI system is Coulomb, or capital C. So we divide it by C squared, and that is the unit of this fundamental constant. Okay. Now, one more thing about charge that we should keep in mind. Unlike masses, there is a strange thing about charges, and that is charges are quantized, the so-called quantization of charge. Now, what exactly does that mean? It means that according to our observation, all charges are multiples of a fundamental value. This value turns out to be E. That's the symbol we designate, equals to about 1.602 times 10 to the negative 19. Okay, Coulomb, very, very small. This is what we call elementary charge. It can be positive or negative, by the way. Okay, for the electron, it turns out the charge carried by the electron is negative E. And what about the charge carried by protons? Each proton carries a positive E. So the charge of the proton and the charge of the electron exactly cancel each other out. And the quantization of charge means that all charges must be an integer multiple of the elementary charge, positive or negative. This is a unique thing about charges. Masses do not have to be quantized like this. There is no such thing as elementary mass, but there is such a thing as elementary charge. And again, the question is why? And again, the answer is we don't know. Okay, so you see, even though we're studying only the first chapter, we're already encountering two fundamental mysteries of nature. And one is, why does nature choose r to the power negative 2 so often of both the gravitational and the electric force? And secondly, what's so special about the elementary charge that everything must be an integer multiple of that? We do not know the answer to these very basic questions yet in physics.